When dissolved in water, a strong acid dissociates completely. And by acid dissociation, we mean the reaction of the acid with water, with liquid H2O. And this is an important point that I'm going to come back to again and again in discussions of acid-base chemistry in this chapter and the next. Unless we've added hydronium in the form of a strong acid or hydroxide in the form of large amounts of a strong base to an aqueous solution of an acid in water, the major process occurring is the reaction of HX with H2O. H2O is the dominant species in the solution, which we can see, for example, in a transparent solution of acid. Most of the substance is still water, and so water is going to be the major reactant in processes occurring with the acid in solution. So in any event, because we're looking at an acid here, HX is going to transfer a proton to H2O, and we're going to end up with X minus, which is aqueous, and H3O plus, also aqueous. And for a strong acid, this is going to be a process that goes completely in the forward direction. So what we can do then here is replace this reversible arrow with an arrow indicating that the reaction goes to completion in the forward direction, something like this. What this means is, if, for example, we're tasked with determining the pH of a solution of a strong acid, to do that, all we really need to do is look at the concentration of HX that was added into the water to produce the solution, translate all of that into H3O plus, and then, if necessary, convert that concentration of H3O plus into a pH by just applying the negative log. So that's a pretty straightforward process that really relies only on stoichiometry. When the acid gets weak, however, the situation becomes more complicated because this reaction of the acid with water to produce the conjugate base in H3O plus is no longer complete. It no longer goes only in the forward direction. It's now reversible. So the aqueous acid can react with liquid water to form the conjugate base, which in this case is A minus, and hydronium, H3O plus, in the forward direction. However, to a large degree, A minus and hydronium can combine to reform the acid and H2O. So this is a reversible process in which the forward direction may not be favored. In a typical solution of a weak acid in water, we're going to have the acid molecules or ions, HA. We're going to have small concentrations because of the fact that this reaction doesn't go forward very much, small concentrations of hydronium and the conjugate base of the acid, which is A minus. And then we're going to have a very small concentration of hydroxide ions. Do keep in mind that hydroxide ions are always going to be present because the product of the H3O plus concentration and the OH minus concentration is equal to Kw, which is a finite number, right? So provided H3O plus is a finite number, OH minus must be a finite number as well. We're always going to have some hydronium and hydroxide in any solution of water, whether an acid or a base or anything else has been added. So that was sort of a qualitative model of the species we find in a weak acid solution. This acid dissociation reaction doesn't go forward very much, and so we end up with mostly the associated acid, HF for example, in solution, along with water, a little bit of hydronium, and a very tiny amount of hydroxide. To model this quantitatively, we can return to the ideas of chemical equilibrium that we saw in the previous chapter. Specifically, what we can do is we can look at the value of the equilibrium constant for this acid dissociation process, which is defined as, do note that this is a definition of the reaction between the acid and water. And just a little correction here, the acid should always be aqueous in this process. This equilibrium constant has a special name. It's known as Ka, and the general reaction associated with any Ka value is always, again, the reaction of the aqueous acid with liquid water to produce the conjugate base and hydronium ion. Recognizing that we can write the equilibrium expression for Ka the same way we would write any other equilibrium expression, we can see that the magnitude of Ka is essentially a measure of how much hydronium ion is in solution when the solution is at equilibrium. So in other words, the larger Ka is, the larger the hydronium ion concentration is for fixed values of A minus and HA concentrations. That's the beauty of Ka. It allows us to go from, for example, an initial concentration of acid to an equilibrium pH value. And because acid-base reactions come to equilibrium so quickly, the equilibrium pH is the pH we're going to measure the vast majority of times in the laboratory, for example. So we can predict laboratory pHs, we can design solutions to achieve a particular pH, and that sort of thing. Ka values can span a very large range. The weakest acids might have Ka values as small as 10 to the negative 50. These are very, very weak acids, and the values tend to increase from there, 10 to the negative 40, 10 to the negative 30, for example, all the way up to what we traditionally call the weak acids, which might have Ka values 10 to the negative 10, up to something like 10 to the negative 3. And then we get into strong acid territory where the Ka value is actually greater than 1, and the product side of that acid dissociation equilibrium is favored. So we can have Ka values as large as 10 to the 7th and 10 to the 10th as well. So huge range spanned by these numbers. The exponents, however, tend to have these nice values around negative 50 to about positive 10. What that means is we can use the p function to express the acidity constant or the acid dissociation constant, the Ka, in a more human-friendly form, you might say. So by taking the negative base 10 logarithm of the Ka, for example, we could generate the pKa of 50, 40, 30, so on and so forth, 10, 3, and now that the exponent is positive, the pKa is going to be negative, negative 7, and negative 10 for these last two entries. What we see in this progression is that on the Ka side, the larger the Ka is, the stronger the acid is. Note, however, that the opposite holds true for the pKa. As the pKa decreases, the acid gets stronger. And this is essentially just a consequence of the fact that a negative sign appears in this equation. This slide shows us some examples of acids and their associated Ka and pKa values, with weaker acids listed near the bottom and stronger acids listed near the top. Hydrochloric acid, which is a classic example of what we would call a strong acid, is extremely acidic with a Ka that is well in excess of 1. So this is a highly product-favored acid dissociation reaction associated with this Ka value. The pKa at negative 6.3, just the negative base 10 logarithm of that value. As we move down this list to weaker and weaker acids, what we can see is that the Ka value is decreasing. 4.5 times 10 to the negative 4, 3.5 times 10 to the negative 4, and on down from there to much, much smaller powers of 10, negative 5, negative 8, negative 10, etc. But the pKa value is increasing as a consequence of that negative sign in the negative base 10 logarithm of Ka expression. So the weakest acids down here, something like methanol, has a relatively high pKa value of 15.5.